Okay, so I think my presentation will be a bit shorter. I'm going to talk a bit about comparing TLS and UAV LiDAR for monitoring structure, together with people from Wageningen, the Australian government, CSIRO, and Tampere University. So we've been using QSMs. So QSMs are quantity structural models, which basically enclose single tree point clouds for quite a while now from TLS data. And with this work, we wanted to see, can we upscale this? Can we use drone LiDAR as well? And can we segment the trees and apply the same methodology that we have been developing for about 10 years now on the same point clouds? And the reason why we want to do it, we want to fly, we don't want to do big area mapping with drones, but we want to see if we put in a 1 hectare inventory plot with LiDAR, what's the uncertainty in relation to putting that plot exactly where it is, what would have happened if it was 10 meters to the north or 20 meters to the south or something like this. So here you can see this is a very brief summary of how we normally collect the TLS data in the field, how we do the segmentation, and then how we convert point clouds to cylinder models, so we enclose the points so we can calculate volumes, but we can also look at branching angles, topology, and how the tree is structured. So there's quite a few of these QSM algorithms around now. This is the one that's been developed by Velodyne. And then this is the final model that we have. So we're really trying to look, okay, can we apply this exact algorithm on these UAV point clouds as well? So then we started doing planning this project a few years ago, so I'm more on the TLS side. It was like hard work, long days of scanning. Once you come back to the field station, you still need to download all the data, you need to charge all the equipment. And then the guys from Wageningen, they said like, oh, we got all these drones, we're going to buy this new drone LiDAR machine. So it's, just going to sleep in, we're going to have long breakfast, we're just going to fly a bit, we're going to come back and we can still go swim. So sort of something like this. So in this talk, so I'll quickly talk about the data that we collected last year in Australia. And then there's two things that I want to quickly discuss is, well, how does TLS compare to UAV LiDAR? But also we flew three different LiDAR sensors on the platforms, so how does different UAV LiDAR systems compare? What kind of data does it give you? So the sites are located in North Australia. There's one Savanna site at the Litchfield super site. And then we have a rainfall grader in the transect in North Queensland. These are all turned super sites apart from Oliver Creek, so it also means that they have like fast hour data and a lot of additional data. So this was our typical setup. So yeah, we had a square in the middle, which is 1 hectare. That's our standard TLS inventory of 10 by 10 meter. And then we had different kind of flights. So we had a 300 by 300 meter area which we flew high density LiDAR. So we fly a copter system, so we get about 5,000 to 10,000 points per square meter. And then the plan was to fly 500 or 500 meters square as well, where we get about around 500 to 1,000 points per square meter. So these are some pictures from the sites. So it's a wet tropical site, apart from the one in Litchfield, the Savanna site. This is the Litchfield site. This is a registered point cloud. This is scanned with an interval of 25 meters. So we increase the grid here. Normally we use 10 by 10 meter in a denser forest. We do 25 meters here because there's quite some wind effects in the savanna. So we wanted to minimize the effect of the winds which come in the afternoon. And that's the flux tower. That's the side here. So a little bit of information about the system that we've been flying. So we've been flying the RiCOPTER with a full VUX system. It's just under 25 kilos, and we have about 15 minutes of landing time. We need to fly some figures first, but we have about 15 minutes where I can really turn on the scanner and collect the data. So these are some pictures. It took us about 6 months to sort all the paperwork and to get all the permits. Even though it was quite remote sites, the rules were changing all the time. The problem was that we didn't have a pilot with an Australian license and all that kind of stuff. But in the end, we were quite successful. We collected most of the data. Sometimes we couldn't fly the full 500 by 500 meters because we needed to have a line of sight and we had to have a takeoff spot that we could actually start from. So sometimes we had to take off from the parking lot nearby. In Litchfield, we could actually just take off in the middle of the site. So there we have full coverage of a 500 by 500 meter. These are some of the products. So this is just height colored. So, well, of course we have an area that's bigger than 500 by 500 meters because we have a 230-degree field of view. There's some cross sections from it, and you can already see that there are some big differences. So this is tropical savanna, and then these are the three denser tropical sites. We get a lot of points, but you can see that really in Rotten Creek, for example, we don't have a lot of points on the stem structure, which is, if you want to do volumetric estimate, it's quite important. So how good do the QSM models work on the TLS data? So this is a tree from the Litchfield, so the Savanna site. So actually our best case scenario is it's quite sparse. You actually do get a lot of hits on the stems, and if you look at the point cloud, you would visually say, well, the whole structure is covered. But we have a lot of problems getting the right QSM fitted. And one of the main problems is that the point distribution is very different because of the different field of view, like we heard in the previous slide. So we get a lot more points in the top. We still get the hits at the bottom, but the algorithms are used to have the density in the reverse way, so the modeling approach doesn't really work where we want it to work. So instead of trying to fine-tune our algorithms, we're really thinking that we should take a step back and just design it from scratch, design it for the data, that it fits the data, and not just try to make it work as best as we can. So this is a little bit of extra work that we did in the Netherlands on trees there. So these are the same trees. So the bottom row is with TLS, this is with the same LiDAR system, and this is some conifer trees. So this was also leaf on, so we stripped the leaves and we made the QSMs, and you can see that there's a lot more cylinders in the top for the UAV LiDAR data compared to the terrestrial LiDAR data. And this essentially gives you the TLS data and the UAV LiDAR data, and you can see that, especially for when trees get larger, when you have more material in the canopy, you systematically start to overfit the volumes, and you create artificial volumes. So there's really still some work to be done if you want to use this QSM approach to estimate biomass. Then we also, in the Litchfield side, we were quite lucky that Queensland, the Australian government was switching some of their equipment. So they had a Velodyne puck, and they bought this Quanergy M8 system, which they had on the DJI M600. And then we flew our systems to the full VUX, so we could have a comparison. And additionally, all the turn sites have airborne LiDAR coverage, so we could also compare to the airborne LiDAR. So this is a cross-section of this Litchfield site. So on top you see the airborne LiDAR. This was before they built the tower. This is the VUX system. This is the Quanergy M8, and this is the Velodyne puck. So you can really see that there's a big difference in the VUX system compared to the systems that are a bit cheaper. If you look at the terrain model and the canopy height model, you can also see differences. So this is the RIEGL. You can really see the roads very clearly. And you can still detect it a bit on the Quanergy M8, which is a newer system that they bought, but on the puck it's very hard to see any of the micro topography in the site. So this is a comparison just for a single tree, just to illustrate how much extra data you actually get. You can't really see properly, I think, but there should be 1,000 points here. For the airborne LiDAR, there's more than 200,000 for the VUX system, 35 for the Velodyne puck, about 100,000 for the Quanergy M8. And this looks good, but as you've seen before, the method that we currently have to process this data, they're probably not well suited to deal with the difference in point density top to bottom that we have with the terrestrial systems. So this is my wrap-up slide. There's also a lot of other drone systems, like the structure for motion, that a lot of other people are doing. There's also the fixed wing systems, which are more, they're flying faster, so they collect a little bit data that's less dense, so it's more leaning towards the airborne LiDAR. But this is really, if you want to do small scale upscaling, so going from 1 hectare to, let's say, 10 hectares, this is kind of the UAV LiDAR system that we're talking about. Speed is way faster. You can just do 10 hectares in half a day. Whereas typically in a normal tropical site in a 10 by 10 meter grid, we budget about 1 week, so it's like 5 days getting 2 days buffer. The quality, the TLS is superior. I mean, I see that still as our reference. It's easier to use. That's sort of, maybe I should have just put it a 1+. It's of course a lot harder to train a pilot and to get all your permits, and if you fly a RiCOPTER system, it has batteries that are very hard to get to places. But if you want to process your LiDAR data, depending on what you want to do with it, you also need a lot of skilled people, and it's sort of a steep learning curve sometimes for some of the algorithms, especially the segmentation algorithms. It's easy to fly. If you want to look at changes through time, probably UAV systems is better because you can easily go out, you can scan again once you have all the paperwork in order. Larger areas, but it's still pretty new, the whole UAV LiDAR data. It looks good, but I think we're not there yet that we can really get as much out of it as we can with the terrestrial LiDAR data. I'm not saying that the TLS is a very finalized product. There's still a lot of development there needed as well, especially to make it more operational, but I think we're definitely further on the TLS processing than we are on the drone processing. Thank you.